The groundwater notes. Doing a little bit of a review just with the water cycle. You've got some boxes that you need to fill in on your notes. And basically, if we start here in the ocean, we're going to move up into the clouds, and then it comes down out of the clouds, down the side of the mountain, and back into where it is stored. So, we've got storage in the oceans. You evaporate from that storage place. You get condensation in the clouds. Condensation are the clouds, basically. Comes down here. You get precipitation out of the clouds. The water runs down the side of the mountain, so just runoff. And you can also have ground infiltration, where it goes down into the ground, just like a filter. Filters down. Some more freshwater storage here. That would be a lake. Discharge out into the ocean, like a river going out into an ocean. And then again, here's the storage in the ocean. What is groundwater? It's water that seeps down into soil and fills in the spaces or pores between soil particles. In the U.S. alone, groundwater supplies 1/5 of our freshwater needs. And then here's a picture of just water coming out of the side of, looks like maybe there's a road here, some ice. Water in the ground, porosity, deals with the percentage of open spaces in a given volume of rock. So porosity is just the amount of space between particles. Good porous rock have spaces the same size particles and are permeable. What influences porosity? Particle shape and sorting. Rounded materials have a lot of space between them. The percentage of pore space is greatest in well-sorted materials, that is, materials of similar size. So if you think about a whole bunch of basketballs and you try to put them all together, all the basketballs are the same size, the same roundness, and you try to put them all together flat on the floor, you're going to get a whole bunch of space between each of them because they don't sit together well, because they're all rounded. You're going to get a whole lot of holes in between. Some definitions. Permeability is the rate at which water passes through the pore space of a rock. Permeability increases with grain size. Large grain materials have large pore spaces. Like sand, we talked about as having, that's the largest size grains versus silt and clay. When you put sand grains together, it is very permeable. Think about the beach. You can get sand wet on the edge of where the ocean is. Versus impermeability is a material that water cannot pass through, like clays and shales, because they're so small, they're very fine-grained, they fit together very well, that water can't pass through it easily. So we call it impermeable. And there's some space here, you can write this stuff out, but you don't really have to write it out word for word. Try to summarize so you're not writing a whole bunch. What is the difference between porosity and permeability? We've already talked about porosity as being the amount of open space between the grains or the particles, and permeability as being the amount of water that can fit into that space. So that's what I would tell you to put down here. Porosity is the amount of space. Permeability is the water that can go into that space. And then we got a picture here. If you have small, well-sorted particles, which means they're all the same size, water can't go through because all the particles are stuck together really well. Whereas if you have larger, different sized particles, it leaves more open space and that water can come down through. So this would be permeable. This is impermeable because no water can go into it. Let's take some time out to understand soil porosity and permeability. So you've got these 3 different pictures on your notes, and we're going to fill in the levels of permeability which also will tell us the level of porosity. So we've got these little grains here, and they're spread apart, they're large, which leaves a lot of room for this water to come in and go through. So that means it's high porosity because there's a lot of space, and therefore high permeability. So lots of water can get in because of all that space. The next one's going to be medium porosity and permeability because they're not as big, they're not as spread out, they fit together a little bit better, so it's harder for this water to come through because they fit together better. The last one, they're really close together, so it's going to be low porosity and low permeability because they all fit together really well, and it's hard for that water to come through and get over here to the other side because they fit so well together. An aquifer. An aquifer is a body of rock through which water flows or is stored. And here's a picture. We've got, here's a well, here's a dry well because it's in an impermeable layer where no water is going to be. The artesian well is down into the aquifer, and aquifer is stuck between these two impermeable layers. So it's a body of rock through which water flows, or in this case is stored, because they have that well that's drilled all the way down into the aquifer. An efficient aquifer is one whose pores are connected and water is able to flow freely. If you get an aquifer that's just stuck between two impermeable layers and it doesn't ever get any new water, it's going to dry out soon. Regions of groundwater. The zone of saturation is the layer of ground where all pores are filled with water. If you think about a sponge, if you saturate a sponge, it's completely full of water and you can't get any more water in it. That's like the zone of saturation here. It's filled with water. The water table is the upper surface of the saturation zone. So that's the top of the area where it's saturated. That's just what we call the top of it, is the water table. And the zone of aeration, which is between the water table and Earth's surface. I always say the zone of aeration is full of air. There's no water there. It's just dirt. How does groundwater move? Certain things influence the movement of water. The permeability of the rock in the saturation zone, or how much water can get into that rock layer. The permeability of the aquifer, which again is how much water can get into that space. And the steepness of the slope. If it's a really steep area, water's not going to be able to be stored there because it's so steep. The water's going to run down to the lower areas. The topography. The water table usually parallels the contour of the land. And here we've got a picture of what's called a perched water table. Here's the top of the land. Here's the main water table, and the only way the water is going to get up into this area because of this impermeable layer is when you have a whole lot of rain and it sort of floods a little bit. The water table is going to come up and rise and rise and rise, and then you get water here. And then when the water table goes back down, this is going to go away if you drill a well into it because it's under that impermeable layer. Conserving groundwater. The principal source of irrigation, waste from industries, fertilizers, pesticides, salt from the oceans will all pollute our groundwater. So we don't want any of that anywhere near our groundwater. How can we conserve groundwater? We can discourage excess use of water from the water table and recycle used water. Some people, when they rinse out containers or something like that, you might save that water and you can go outside and water a plant with it instead of turning on your spigot outside. Wells and springs. A well is a hole dug into the water table that fills up. Water must be pumped to the surface, whereas a spring is a natural flow of groundwater that flows to the Earth's surface, so it doesn't have to be pumped. And here we've got a picture. The saturated zone, here's the water table. This triangle here is the sign for a water table. So you might want to write that down on your notes. And then you have the unsaturated zone, or we call it the zone of aeration because there's no water up here. This water table is paralleling the layout of the land, and then comes out here into a pond. They've dragged a dug a well, here, and it's full of water. And then you have this impermeable layer where there isn't any water. An artesian well, wells in which water spouts out of an aquifer due to pressure from the surrounding water. And here's one, there's a whole bunch of pressure that's built up down here, and then all they've done is tapped this into that well, and then it just spews water out. A hot spring, heated water from below Earth's surface that rises to the surface. There are a lot of these. If you think about Hot Springs, Arkansas, they do a whole lot of spas and that sort of thing right around these hot springs. A geyser, a hot spring that periodically erupts, just like where in the U.S. Hopefully you're saying just like Yellowstone. That's what this picture is here. We've timed Yellowstone to know when it's going to erupt. It's under so much pressure, and it builds up steam, and that erupts. Groundwater and weathering. Hard water is water with large amounts of dissolved minerals. A lot of the times it's going to collect around the faucets and that sort of thing, and when you clean, you have to use a special cleaner like CLR or something like that. Whereas soft water is water with few dissolved minerals. When you wash your clothes with that sort of stuff, sometimes it still feels soapy even though it's really washed out. Cavern formation. Carbonation causes rock to weaken and weather, which fractures join to form caverns or caves. And this is a picture here. You've got a little stream. It's eating away at the rock underneath, eats away a little bit more, eats away some more, and eventually you wind up with a cavern underneath. You see this water flowing through, and then it's suddenly gone because it's going into this big hole that it's made underground. Sinkholes form when the water table is too low and caverns are no longer filled with water. You can see here there's a road here, there's the other side of the road, and this sinkhole has created, and it's just sunk down this whole area. Stalactites. Water drips from the top of caves, and then the calcite solidifies. Stalagmites are dissolved calcite deposits that have built up on the floor from the dripping from the stalactites. And in your notes it says something about a mnemonic, but the way that I'm going to tell you how to remember it is that stalactites have the C in it, and ceiling starts with C. So stalactites come down from the ceiling, or stalactites hold tight to the ceiling. I've heard some people say that. Stalagmites grow up from the ground. Ground, stalagmites, ground. Put it together that way. And here are some pictures of caves. And karst topography, regions where chemical weathering occurs because of groundwater. And again, here's another picture of a cave. We've dissolved the rock around it. And karst topography is mainly known to be in these 4 states, and that's what those 4 blanks are on your notes: Kentucky, Tennessee, Indiana, and Florida. Again, Kentucky, Tennessee, Indiana, and Florida. We do have some karst topography in Virginia, but it's not one of the biggest states that's known for it. Here's some more pictures. And here, last thing on your notes, label the zone of aeration and the zone of saturation. So which one is filled with water? That would be the saturated one. And here's the water table. So any land above the water table is going to be filled with air. So that would be the zone of aeration. Again, I really recommend that you try to remember it as a zone of saturation, like a sponge filled with water, and the zone of aeration is filled with air.